Just a little down today. Hey, already some likes. Allotropy, yes. How's the audio quality, YouTube? How is the audio quality? I feel it might be a little too sensitive or a little bit low. ठीक है. I think we can start. Okay, not that. ठीक है. Let's start. So we're gonna start by talking about carbon. Now carbon has 6 electrons. Let's try drawing that. Carbon, and you have 1 and then 2. One, 2, 3, 4, 5, 6. ठीक है. Basic carbon atom, and this is it, right? Now there's some things about carbon, how it behaves and everything. Now we've looked at some chemical properties of carbon. Hello Risha, how are you? Some chemical properties we've looked at. Oh, you can't see the screen because I was gonna say a bad word. I'm sorry. Yeah, I didn't start my screen sharing. It's on YouTube. They can see it. I forgot to open it on Zoom. Sorry. Okay, we're looking at carbon. It has 6 electrons, and we've seen some chemical properties of carbon. Okay, for one thing, combustion. Can you guys think of any other chemical properties? What do you guys think? Not really, I guess. Any physical properties that come to mind for carbon? There's a lot of noise. Can you guys see my screen now? Is it fine? We're trying to do different allotropes of carbon and a bit on nanoscience. ठीक है. Okay, ठीक है. So carbon, how we see it is like how it ends up behaving in our lives is, for one thing, it varies a lot, and the other thing is it just, because it varies a lot and it does so many things, it becomes very important to us in many different ways. One such way, we'll study like how it bonds first, and then we'll move on to explaining different types of things. So let's take a look at carbon bonding with, let's say methane. Let's talk about CH4, carbon bonding with methane. What's interesting about carbon is it can create 4 bonds, and if I want to draw a dot and cross of carbon with hydrogen, this is it. ठीक है. ठीक है. A really poorly drawn dot and cross of methane. It's called, this molecule is called methane. Carbon is bonded to 4 different hydrogens. ठीक है. Now, because it can get a bit more complicated, we'll represent each bond with a stick or just a line. Just a line. We'll replace the electrons shown with just a line. Why did it do that? Why didn't it do that? ठीक है. And this is what methane looks like. Okay, easy, straightforward, nothing special here. This is just methane. Okay, now because of carbon's, you can't really call it special properties, but like how abundant it is and how just the, I guess let's call it some certain properties for carbon. What it ends up doing is it ends up acting like Lego pieces of Legos. What do I mean by that? Now, a carbon can make 4 bonds, up to 4 bonds. Is it a covalent bond? These are covalent bonds, yes. This is a simple covalent structure, right? And because in the dot and cross, in the dot and cross, you saw the electrons are shared. I didn't draw the shell, right? But you saw they were shared rather than exchanged. So it is a covalent bond. Okay. Okay, they end up acting like Lego pieces. What do I mean by that? Now, a carbon can also bond with itself with either a single bond, a double bond, and even a triple bond. So up to 3 pairs of electrons being shared over here. Okay. But it can form a double bond and it can form a single bond. And spam, yes, if you've seen this before, carbon double bonds and carbon, probably not a triple bond, but it can do it. Have you guys seen this? I think you guys have. Spam yes or spam no if you have or haven't. Let's make that a bit quick. Okay, yeah, okay, fine. Take it. Seen it. Triple bond as well. Yes. Okay. So how carbon ends up like bonding with other things and especially itself. You've only seen it till double bond. Yeah. Triple bond is like we don't even study it too much because it doesn't show up as often. But this is probably the most important one. How it's different is it could end up making. Now, why I say it can act like Lego pieces is because of something like this. It can do a wide variety of things. And you've seen some weird things carbon do, right? Now, it can make graphite, if you remember. It can make diamond structure. And it can also make something like this. What? I'm just trying to show you how flexible carbon is, how many things it can do. And it's the same methane molecule. It's very similar, but what's happening is all the carbon in the center is all bonded to each other. Okay? And every other bond is with a hydrogen. Okay. And over here you can have a double bond or a triple bond even, but a very unique thing. Now at this point, many people ask, so that's pretty cool. How long could this get? Is a valid question. It shows up a lot. Okay. And what do you guys think? How long do you think this chain can get? What are your thoughts? This is part of O levels. Very long, and yes indeed it does. Hundreds, thousands even. It can go very long. Let me try showing you a few examples. Let's come over here. Okay. This is the first one I drew, methane, carbon with 4 hydrogens. Okay. This is what it looks like. This is carbon in the center, the colored one, and tiny little hydrogens around it. Now it's shown in this way, it's written in this way to show the bonds because it's easier to highlight the bonds this particular way. But it's in real life, its shape is kind of unique. All bonds, like this is planar, so all bonds are at, shown at 90 degrees, but in real life that's not true. In real life, they're trying to be as far away from each other as possible, and this is kind of what it looks like. Okay, and here's an ethane molecule, right? 2 carbons. You don't have to worry about the names as much right now. And then you have more. Notice how the carbons are going in a zigzag of sorts. And if there was a diagram of this particular molecule I've drawn over here, I've written down over here, the other, like, it would keep on going on and on like that if I kept adding carbon, and each dent or node, you can say, would be a carbon atom. Take care, following so far? I just want you guys to absorb this as much as you can, right? We're not doing anything technical. We're doing allotropes of carbon. We're just talking about, could you please zoom into it? Is that okay? Do you guys understand a bit? Any confusion so far? Something's wrong. My screen seems to have frozen. Okay, that's fine. It's not letting me zoom in. I'm sorry. I don't know why that's all clear so far. Okay. Okay. So this is just to show this. These are examples. This goes under organic chemistry, which we'll start soon. Okay. These are known as hydrocarbons. These are known as hydrocarbons because they have hydrogen and the molecules with hydrogen and carbons in them. But this is a good way of understanding the flexibility of carbon, how it can do many, many things, right? It can make these chains, it can make carbon dioxide, which is just a gas, methane over here. Actually, all of these are gases. And these chains can go as long as, thousands, if not more than like tens of thousands of carbon atom long. Okay. Now these are the basis of, organic chemistry. Hydrocarbons fall under organic chemistry. And organic chemistry has to do with, you can think of it as the basis of biochemistry. Okay. Sablal does teach on Mondays, but he wanted me to take today's class, so here I am. Okay. So what's happening is, organic chemistry mein, you deal with a lot of hydrocarbons because most of these organic molecules or anything in it is based on a hydrocarbon or something very close to it. Okay. It's all carbon based. So our biology is all carbon based. Now let me give you some examples. So human beings are known as, or like life on our planet is known as carbon based life. So everything in our body is primarily carbon based. Okay. Our proteins, our fats, carbohydrates, you've heard of it, they're all carbon based. Even the base of our DNA is, carbon is used there. Okay. And one good evidence of carbon that there's a lot of carbon in living organisms is, have you guys heard of fossil fuels? Fossil fuels. You've heard of it? What are fossil fuels and how do they get there? I like asking questions a lot, so it's more discussion based, but I think people just take a lot of time typing. Maybe we can enable voice chat. Yeah. I like what Haya's saying. Okay. Now what happens is when like plants, animals and everything, they die and they get, what's the word for it? They end up going underground. What's this better word for it? I can't remember. Anyway, all of that, all of their bodies decay, and over time, just only the carbon and carbon-based things are left behind. So you get in fossil fuels, they're literally corpses of, old dinosaurs and whatnot. I keep saying dinosaurs, but they're just all organic, millions of years old, organic life, which we're extracting and we burn it as fuel. So in it, you have fuel in it, you have coal in it, and anything that's carbon-based. Fuels are normally, this is methane, this is your SWE gas, which is a fossil fuel. Ethane, you don't really use it as much. I haven't really heard of it. You have propane tanks. Now, if you've ever gone to like a restaurant where there's a big tank and they're burning something, like especially if you've had a burger with a cylinder next to it, heating the thing. So that cylinder, that very round looking cylinder with gas in it, it's not methane or SWE gas or natural gas, it's actually propane. Okay. Propane is also used, and you have something like octane, which has 8 carbons. That's your petrol. 1, 2, 3. I can't draw it here. Let me try drawing it. 3, 4, 5, and 6. So you have up to 8 carbons, and everything else around it is just hydrogens. Okay, and that's propane. Octane. I'm not drawing the hydrogens because it's going to take a lot of time. But does that make sense? So I'm just highlighting how versatile carbon is. Let me show you more molecules that are carbon-based. Okay. Here you have methane turning into ethane, turning into 1, 2, 3, 4, 5, 6, 7, 8, propane, octane. I keep calling it propane. Okay, this is petrol. This is what it looks like. Now the hydrogens, they're not showing it because the molecule is already really complicated. But you can understand that this chain can keep on going. And it does. Okay. And here's something that's you might have seen in biology. Let me try taking a neat screenshot of this. Screen grab. It's not going to be a good screen grab. Okay, this thing. And this is a fat. This is a molecule of fat. And these are all just these carbons bonded to each other, surrounded by hydrogens, like this. And they're all joined together to make this particular molecule. And this is literally a fat molecule. Okay. And here's more. Here is DNA, rDNA, right? And this is also carbon-based. Now, you can't tell the carbons because they're tiny and the diagram is very... I can zoom in, I forgot. But I can make it bigger. For some reason today I can zoom into pictures. And these are just chains of carbons going around with important other atoms attached to it. And that's literally our DNA. Are you guys following? Does this make sense to you guys? So our fats, proteins, even our DNA, it's all carbon-based. And if you thought diamond and graphite were complicated things that carbon can make, carbon can do a lot more. Okay. Are you guys following so far? It's like straight. Okay, you guys are already saying yes. Okay, never mind. Okay. I hope you guys appreciate how versatile carbon is, because we'll be looking at a bit of that versatility. Okay. Okay, so we're gonna discuss some allotropes of carbon. Now, what are allotropes? You guys know this? So they're different structural forms of the same element, different physical manifestations, structural forms of the same element. ठीक है. Is there any allotropes of carbon you can eat? I should kind of hold right there. I went over this a bit of organic chemistry because I think it's wicked cool. I was going over these diagrams. I wanted to show you because you appreciate how carbon works when it comes to organic chemistry, right? So I wanted to show you a bit of introduction on organic chemistry, how atoms and how molecules end up looking like, and how versatile, and literally, you know, I'm not even joking when I say carbon acts as a piece of Lego. And you can probably tell it does. By the time you reach fat, it does, right? But after this, we're going to put a full stop in compounds of carbon. And we're going to look at allotropes right now, because some allotropes of carbon can also do some interesting things. And that's the topic of discussion right now. Okay. Now, these are carbohydrates. They're not allotropes of carbon, because allotrope of carbon would be just carbon in it, right? These are organic compounds. They're called hydrocarbons. Let's go back here. Allotropes would be something like graphite, which you know and love, and diamond. These are the two most common examples. ठीक है. Yes, let's take a look at diamond first. Do you guys understand what an allotrope is? It's just different forms, because graphite is just carbon atoms joined together, you know, in a particular way, and diamond is also carbon atoms joined together, but they're drastically different in their physical properties, right? And they're different because how they're chemically arranged. Let's take a first look at diamond, because it's as expensive it is, it's probably the most boring, because it does absolutely nothing. It's just very hard. Okay, this is the structure of diamond. And again, I can zoom in. Why do I fall into this trap? Sorry guys, today I just cannot zoom in. Something is wrong with my devices today. I'm trying to zoom in as much as I can. Okay, this is a carbon atom in the center. Over here. And it's bonded to 4 other carbon atoms. And each of these carbon atoms are further bonded to 4 different carbon atoms. And the structure, even though it looks pyramidal, it's just here to show you, appreciate how the structure is drawn, but the entire structure isn't drawn in front of you, right? And this is what diamond looks like. Let me try looking at another picture. It's one nice one. Yeah. If I can... Bring this here. Here's another view of the same diamond. Okay. On top it's a small part of the structure. At the bottom, this is how it really looks like. Okay. This is similar to that. And it's all just carbon. Now all of these bonds are single bonds, right? So there's a carbon, or there's an electron being exchanged or shared between both of them, and they're covalent bonds. This is an entire covalent compound, right? So it gives it special properties. One, is this a complex molecular structure? Well, it is complex because it looks complicated, but it's not, you don't call it complex. You call it a giant molecular structure. It's a giant molecular structure. Yes, okay, yeah, okay, TK, you know it's a giant. Yes, exactly it is. TK. And people are confused with that term, and we should bring it up in a bit. TK. Now, this is literally, so you can imagine all the carbon atoms in a piece of diamond are all bonded to each other through covalent bonds. It doesn't have intermolecular forces. It doesn't have, metallic forces with a sea of electrons. Every atom in the in a diamond, in a piece of diamond, is all bonded together with covalent bonds. And covalent bonds are some of the more stronger bonds in chemistry, right? They're really strong because you can heat things so much, like you can heat water, it turns it into a gas. You can superheat it. If you pressurize it, you could take it up to really extreme temperatures, but it does not, the bonds do not break, right? Only at very extreme temperatures do the bonds break. And by extreme, I'll say, I think they start breaking at possibly 3000 degrees Celsius. So because they're all giant covalent bonds, and this is a giant covalent structure, it's very difficult to melt, misspelled there, to melt diamond. Because to melt diamond, you have to start separating its particles from each other, or make them loose enough they can start moving. And for a diamond, that means you have to overcome the carbon-carbon covalent bonds, which are again extremely strong bonds. So that's why diamond will have a very high temperature. Does that make sense to you, everyone? Diamond will have an extremely high melting point / boiling point. Do you guys follow this part? Hi, the lover. Hi, the lover. How are you? Chica? Okay. Is this a little too easy? Should I move like a bit faster in this? What do you guys think? Hey, 4 likes. Speed is fine, but Mesam always says speed is fine. Okay. So what other properties of diamond do you guys can think of? Diamond has a very strong, it's just very hard, it's just very strong. And it's very strong is because when you have a piece of diamond in front of you, I kid you not, if you have a piece of diamond in front of you, how do you draw a piece of diamond? Something, okay, that's not a diamond. Yes, I want to undo. If you have a piece of diamond, kind of like that, right? This entire thing you can consider as one molecule. If you're holding a piece of diamond in your hand, it's literally a molecule of it. And that's why you call it a giant molecule, because it's literally a gigantic molecule, because you can literally hold it in your hand. And it has insanely high melting point, boiling point. And there's no free moving electrons over here, so it cannot conduct electricity at all. It's an insulator, very high melting and boiling point, again, very hard, right? And it's used to cut glass and other less hard things. I think you guys know diamond is used to cut glass because it's harder things are can very easily cut less hard things. And I say less hard because you wouldn't call glass soft. Okay, is that clear so far? Is that clear so far? Haya's the only one who agrees, who says yes. I'm kind of disappointed with everyone. So this is how carbon bonds with when it is making 4 bonds. Okay. Over here we saw it in diamond, and we were seeing it in our little brief introduction to that organic chemistry wala part, how versatile it is. But carbon also does something special. Again, as long as so what it already did wasn't enough, it can make these little hexagon sheets. Okay. And to save some time, this is what I'm going to do. How many of you know where this is going? I'm gonna erase this because it looks weird and join this together like that. Okay. And over here it's incomplete, but over here you see carbon making 3 bonds, and each carbon is actually making 3 bonds. Let me try completing this a bit so people understand it better. You know, each carbon makes 3 bonds in this particular case. And so it's a completely flat structure. This is hexagonal, so it's literally a flat structure, and it ends up making a sheet which goes for millions of carbons, right? It's going to be a really long sheet, but this is the structure of it. And yeah, have you seen those gates, like with you know, the crosses on it, how metal wires are woven around it, especially for apartment gates? If you've seen these gates, imagine this like that, how the fibers are woven in, RNK wires are woven in, but in a hexagonal fashion rather than a square fashion. And you'll understand what this exactly, you can picture it really well. Okay. Now, again, because how it looks different, it will have drastically different physical properties. One thing is it's much weaker than diamond structurally. Why is because, and it's very slippery as well, and both of those properties go hand in hand, because you have these sheets of carbon and they're not bonded to each other, but each carbon is attracting the other sheet, kind of like intermolecular forces. They're attracting each other. Okay, there's attraction between them. But if on impact these sheets can slide over each other, aage piche ho jate hain, they easily slide on top of each other. That's a good question, Mesam. I'm going to get to the 4th electron in the outer shell. I wanted to kind of talk about certain properties, then move on. So they slide over each other, right? And because they slide over each other, it makes it feel very slippery. So if you pick this up in your hand, this particular form of carbon, note how I have not said what it is. If you pick it up and if you kind of play with it between your fingers, it'll feel very slippery, because when you're doing that, these sheets of carbon are sliding on top of each other, making it feel very soft and very slippery, right? And because Mesam asked, I'll try answering it. Mesam's absolutely right. What's happening to one electron that's missing? Because this carbon has 4 valence electrons and it can make 4 bonds. Over here, each carbon is making 3 bonds. So what's happening to one electron? That one electron on each carbon is around the carbon, and it's not really doing anything, so to speak, and it's free to move around. It's kind of delocalized. So it's free to move around on top of these carbons. Okay. And if it's free to move around, what kind of physical property would that allow this particular allotrope of carbon to have? It's a conductor of electricity. So it can conduct electricity. Okay. So what I'm talking about is this particular structure is for graphite. Have you guys heard of graphite before? Yeah, conduction. I like how people are excited. You have heard of graphite? Where have you heard of graphite? Oh, pencils, okay. Do you know the lead in the pencil can conduct electricity? Have you guys heard of that? Yeah, or you guys have probably done that experiment as well. So yeah, what you do is you shave the pencil off, right? Halfway in between, and you put, like, you make a circuit and you make two wires touch it. And what you do is the closer the wires are to each other, the brighter the light bulb glows. And the further they are, because the resistance increases, the light bulb dims down. And graphite is actually a really good conductor, and it goes down because that graphite in the pencil is not pure. It has clay and other things in it. That's why it's not designed to conduct electricity. Okay. Now graphite has one or two very special purposes. One is pencil, it's very commonly used. But graphite, if you've noticed, doesn't really have, even if these slides are allowed to move on top of each other, and these so-called intermolecular forces are there, it's still a very large sheet, and these are like large flakes of graphite, right, on top of each other. So if you hit it, it can move, but if you heat it, you don't really end up breaking too many bonds, because most of it, because these sheets, I've only drawn 3 hexagons, this is probably tens of thousands of hexagons to put together one sheet, because there's so many, right? And they can slide over each other, but that still gives it a lot of thermal resistance. It does not melt. So graphite has really high melting point as well. Graphite has very high melting point, not as high as diamond obviously, but this still has really high melting point. Obviously boiling point is there as well. And the other thing about graphite is it's very slippery. And the third thing about it is very unique, is it can conduct electricity. Okay. Now these two properties make it very important. When you have, let's say, heavy machinery, like big machinery, right? Not your car engines or anything. We're doing allotropes of carbon. And hopefully nanoscience, but this is taking some time. Okay. Whew. Hang on. Now for graphite, those heavy machineries I'm talking about, like big industrial drills, they generate a lot of heat. So one way to avoid that heat is to have lubrication, so to minimize friction between them and also make it more efficient. Now if you try putting oil in there for lubrication in those machines, if you try putting in oil, the problem with oil is it easily evaporates over time. Even if you use very thick oil, over time it will boil away or evaporate away, because the temperatures of those machines is insanely high. That's where graphite comes in, because it's slippery and has a high melting point, it acts as a lubricant. Even though it's a solid and really high melting point, but it's very slippery to the touch. You guys have touched the pencil lead, right, in your palm, in between your fingers, and you can tell it's kind of slippery. And that's impure graphite. It has a lot of, like, I think 50% of it has clay in it, right? But you can tell, you can understand and appreciate why it's kind of slippery. Because every time you touch it, it's slipping between your fingers, and you look at it, you have pieces of black in your fingers, right? Those are sheets of graphite coming off and sticking to your fingers. Okay, does that make sense? This is important. It acts as a lubricant for heavy machinery, or at machinery that are operating at high temperatures. Hi, someone. We're again doing allotropes of carbon. Does this make sense? And for for diamond, it's a good cutting tool. So drill bits, the tip of bits are diamond. So the worst of the drill bit, the main force is on the tip of the drill. So diamond is used there. That's one property of diamond. Right at the drill bit, thoda sa piece laga and then diamond ka. Or any cutters, especially glass cutters, have diamond on top because it makes it cuts really well with diamond in it. Okay. Does that make sense? Everyone following? Does this sound like common sense at this point? Or is this like very alien information? Is this falling into, oh, I understand graphite now. Oh, I understand carbon now. What makes diamond so expensive? Because it's shiny, it's pretty, it's rare. And that's it. People like wearing it. Gold is expensive because it's rare. I read somewhere the total amount of gold on the planet is you can fill 3 Olympic-size swimming pools, right? In the entire world. Like if you collect all the gold, even that's not been dug up, you collect it all out, you fill 3 Olympic-sized swimming pools with it. That's very little gold. And yeah. So here's a way of thinking about it. Arisha asked, what makes diamond so expensive is, have you guys heard about the scalper issue these days? I'm kind of suffering through it. The scalper issue, I don't know how to spell scalpers. I think they're 2 P's. They can be 2 P's. Scalper issue. Do you guys know what's going on with the scalpers? So, because of coronavirus, a lot of industries are not producing the same thing at their usual capacity. You've heard of many industries shutting down, but a lot of industries haven't shut down. A few industries that continued to produce were, electronic companies. And these electronic companies, for one thing that's under my, radar is iPhones and other phones. They're still producing it, but not in the same capacity because of coronavirus. They've limited down production for safety reasons. Another thing is the PlayStation 5 right now. So what ended up happening was these devices are coming out, these processors are coming out, these are new things are being released. What people did was they bought all of them in bulk. They bought it, and it's called scalping, where you buy it and you keep it with you, you hoard it, and you sell it at a higher price. Right? And that's what a lot of people are doing. So no one is able to buy these tech things, and not just, PlayStations and whatnot. A lot of important things. Now I have to get CPUs for a computer. I can't buy them because everyone just bought them off. And they're selling it for, the PlayStation is being sold for $3,000 right now on websites like eBay. And it was released for $500, right? And why am I talking about this is, because the PlayStation is rare in the market and they didn't produce it enough, people who bought it can set their own prices for it. Okay. I don't know about it raining Jupiter, but we'll talk about that in a bit. So it becomes so expensive. That's why things like diamond and gold are so expensive because diamond, especially larger pieces of diamond, are very rare, right? And people really appreciate them because how beautiful they look, and they never go bad. Gold is extremely low in the reactivity series, which you guys know, so it doesn't corrode, and is also very rare, looks very pretty. And diamond looks very pretty, doesn't easily, spoil. You can have a piece of diamond for thousands of years, it won't go bad. So this is essentially what gives something its value. It doesn't go bad, stays with you very long, and needs to be rare, otherwise it's too common. Yeah, Ramis, if you have a PlayStation 5 right now, you can probably sell it for, I know people are buying it for, like in Pakistan, they're buying for like 180,000, 150,000, but its price should have been close to 80,000, right? People can't buy it because it's, so this is how prices are set, unfortunately, in a capitalist world. But enough of that lesson, let's come back to graphite and diamond. Is that understood? Let me show you some more of graphite if I can. I have a very bad picture of graphite, which I'll show you guys. Forgive me for this poor quality picture. This is a top view of the same graphite sheet. Everything's clear? Brilliant. Okay. Now, what they end up doing is they take graphite and they do something more to it. What they try to do is, and you can actually do this at home, and I'll try to explain why if anyone's curious. What they do is they try to form a graphite sheet which is just one sheet. It doesn't have multiple layers together, right? They try to extract as big as possible a sheet of graphite, kind of like how it's shown over here. Okay. And that is called graphene. This literally is one atom in thickness, obviously because it's made up of carbon, and there's nothing else to it. It's just a one layer of graphene. They're just arranged in these hexagons, and it's a repeating pattern. Exactly what graphite is, but just one layer. Okay. Again, it'll have very similar properties to graphite. It won't be soft, it won't feel soft, it won't be a good lubricant because it doesn't have its layers anymore, but it'll still have, a good conducting, it'll be a good conductor of electricity because the electrons are still there, free to move around. The other thing is it'll have relatively high melting and boiling point, but I think it'll be very easily broken or anything because if you have a large enough sheet, if you're holding it in the palm of your hand, it can break very easily because it's just an atom thick. But because it's only an atom thick, and maybe if you had it in your hand, you can break it easily, that doesn't mean it's weak because it's something very thin you're trying to break. Compared to steel of the same thickness, this is like 10 to 100 times stronger than steel. This is very strong because again, they're all covalent bonds. Okay. They're all covalent bonds, and that's it. So graphene is used to make different things. One such thing is if you roll up graphene at 650. If graphene was a sheet of paper and I picked it up from one corner and I started rolling it, it would turn into a pipe which would look something like this. Something like that, if I can cheat and copy and paste. Something like that, if it's making sense. should draw better. Who draws better, Sir Bilal or me? I don't think that's even a fair question. I'll lose. That is really cool, right? And it makes a tube. This is a tube. It's called a nanotube. It's incredibly cool. You're absolutely right. This is a nanotube. He doesn't draw much? Yeah, okay. I think one time we had that experiment class, and that was very good in my drawing skills. But this is like just too many lines to draw. iPad isn't that friendly when it comes to drawing, or this app isn't that friendly when it comes to drawing in detail. Okay, so these are called nanotubes, and they serve a lot of functions. For one thing, because they're all layers, is the same graphene sheet. Graphene sheet is very strong because it's all covalently bonded, and these tubes are like that as well. So that makes graphene and these nanotubes very strong, and by strong in terms of density, because right now if I had the tube in my hand and I try to break it, I could probably snap it in half very easily. That doesn't mean it's weak. You're trying to break something that is just a few atoms in thickness, right? Compared to the same thing, if I had steel with the same thickness right next to it, this would be a joke in front of this thing. This would be 100 times stronger at least, easily. And nanotubes offer you, very good structural integrity, very strong structure with while keeping the weight really low, right? Now you could make aircrafts and everything out of it. The only issue is producing large amounts of nanotubes is very expensive. So you're still happy with, aluminum for airplanes, but you have heard of carbon fiber, which is very similar to nanotubes, not as neat. And you know about carbon fiber, which is used to make, it's very hard, very lightweight. It's used to make Formula One race cars, to car bodies, to aircraft bodies, anything where you need something very lightweight, but like unbelievably strong structural. So for the same weight, carbon fiber is way stronger, and nanotubes is even more strong. But nanotubes are way harder to make than carbon fiber. Carbon fiber is something similar, like nanotubes, but yeah, we're not talking about carbon fiber in too much detail. Now nanotubes, you've actually seen it closer. If you've seen a very good quality racket, those are made of nanotubes or carbon fiber. I think it's a bit of both. So how light it is, and those things are really strong. Like I've never seen a racket break. I guess that's a poor example for it. But a very more important example for nanotubes is for drug delivery. Okay. So how like are you asking it? What is the purpose again? So yeah, so how, you have like a syringe and it's supposed to deliver medicine to your bloodstream directly. What if you wanted to deliver some medicine? Why does that sound so incriminating? How do you mean incriminating? Not that drug as in medicine. Abey yaar. Medicine delivery, fine. Drug delivery, what am I teaching you guys? Okay, Breaking Bad right here. Okay, if you want to have like some certain medicine directly delivered into a particular part of your organ, like completely down to possibly even right into a cell, you can do it using this structure, right? It's very thin, it's a few atoms in diameter, as you can see, and drug molecules can be ferried, I want to say ferried, but not really, can be pushed through this into wherever it's needed. Another structure it can make is called, I need to end class soon. I think Sir Bilal needs to start his other class, which sounds wrong. Okay, another thing it can do, you can literally make balls out of this, like a ball like this. Now on the right hand side, you have a football being compared to a ball on the left, which is all made up of carbon atoms. Now how many? Tomorrow, I think we should do a question, Masa. Let's see, I'll ask her Bilal to continue this, but let's see. Okay, but let's focus on this. This is literally a ball of carbon. It's empty on the inside, only on the outside. There's a football right next to it because it's trying to highlight for after every hexagon, there's a pentagon right next to it, how footballs are arranged. That allows it to be spherical rather than hexagonal and flat, right? So over here, why do you ask, Risha? Do you have a question? Yes, you know the name. These are called buckyballs or Buckminster fullerenes. Buckminster fullerenes. It's one word. Left a space there. Okay. And what's the purpose of this? It's interesting is it's also used for drug delivery. What you do is if you have some important drug, you make the cage around the drug and the drug is on the inside, and this can deliver it to wherever it's designed. It gets complicated, of course, but it's, even my spellings are wrong, but I think yeah. Okay. So this is also used for drug delivery. Let me ask you two questions. What is the chemical formula for this is not my question, is C60, because there are literally 60 atoms of carbon around it. C60, exactly, right? Now my question is this a giant molecule? Is this a giant structure? What do you guys think? A lot of people think it is. Why do you say no, someone? Why not? That's a fair question. End of the day, it doesn't act like a giant covalent structure. Buckminster fullerene is, I believe, a liquid at room temperature. It is a liquid at room temperature. Okay. Because it's kind of so weird to think about this as a liquid, but in real life, this is literally a black liquid at room temperature. I think it's very viscous, which means very thick, but it's a liquid at room temperature. It's not a giant structure. People confuse this as a giant covalent structure. It is not a giant covalent structure. Okay. And yes, exactly, there's weak intermolecular forces between them. End of the day, it acts and behaves as a simple covalent structure, and that's what's important. Okay. Now, to identify a weak versus a simple covalent structure versus a giant covalent structure, you look at, rather than what it looks like, you look at its melting and boiling points. If it's really high for a covalent molecule, it has to be a giant covalent structure. That's why it has that high melting point. Otherwise, it's just a simple covalent structure if it has very low melting and boiling point. Okay, does that make sense? It's 7 o'clock. I have to end it right now, but there's a bit more on this and a few questions. Okay, well, I'll see if I can continue this tomorrow. For now, bye-bye. If you have any question, did you guys have a good lesson? Did you guys understand this? Yes? Was this interesting? I don't think it was too interesting. What are you guys saying? Okay, you don't have to say it. Fine, it was okay. Pretty interesting? Not interesting? Someone doesn't like it? Okay. Yeah. I'll tell you why it's not interesting to me anymore. But when I was learning it, it's easy. The questions are very straightforward. But yeah, let's end it here. Chalo, bye-bye guys. Take care. Bye-bye YouTube. Take care. Thank you for tuning in.